Okay, so this is the third problem from the second problem set of David Tong's lecture notes. So in this one, we're basically showing that the momentum operator, the four momentum operator, after being normal ordered, can be written like this in our Klein-Gordon theory. So we already showed, so P0 is just the Hamiltonian, and we already showed that after being normal ordered, we can write it like this. Which is consistent with this notation. So P0 is constrained to be EP. So we already have done the zero component of this, but we still need to do the spatial parts. So the spatial parts, the momentum, in terms of the fields, can be written like this. And so if we write down our, expanded fields, then we just, we just plug them in. And so you'll have these, you FOIL these things, you get these four terms, and bring out everything in front. And then just like in the Hamiltonian, this first and last term, you'll end up getting a delta P plus Q. And so in the end, by symmetry, in these integrals, these two terms will vanish. So we're just going to throw those away. And what we'll be left with, so again, we integrate over x, or I guess we kind of identify that this integral over dx times its exponentials are like delta functions. So yeah, so we get this. And then we can do the integral over q. And then we just normal order this, move this guy to the right. So then we get 2 of this term, which cancels this one half. And so we get what we should get. So yeah, nothing too tricky. Again, just kind of an easier version of the calculation we did for the Hamiltonian before. And then the last thing we have to do is he wants us to compute this commutation relation between the four momentum operator and the field. So again, we have this operator, and since our 5x, and this is the Heisenberg operator, up here we were using the Schrodinger picture operator. But so here if we do this commutator, so obviously I can bring out the integrals in both of these terms, and I'll just have to worry about the commutator of these things with, so there's two terms in this phi, one involving lowering operator, one involving raising operator. So I can just write it like this, and then use my, rules for 3 things in a commutator, and I get this, and then you can just use our basic commutation relations. So we get delta functions, that enables us to do one of these integrals, and yeah, so we get this, and then it's just a matter of kind of identifying. So P mu is, in this term, it's like 1 over minus I d mu of this exponential, and here it's similar, 1 over I d mu of this exponential. And then you just pull that out, factor out a minus I d mu, and yeah, so you get what you're supposed to prove, that this commutator is equal to minus I d mu phi.